So let's understand the concept of power amplifier here. So what exactly is the power amplifier? We'll see here. So let us say this is a schematic right over here. And this amplifier is indicated by a symbol A. It has a gain of A. And it is operated by a dual power supply. So at one terminal, we connect it to plus VCC, which is positive power supply. And another terminal of this amplifier is connected to minus VEE. So that's the sign convention for the DC power supply we use. We have this input signal. Maybe it's coming from the pre-amplifier. Okay. So it's a VI, and then it delivers it sources the current I into this power amplifier. So the function of the amplifier, which is power amplifier, is to further amplify this signal VI and deliver that amplified signal with much higher signal level to the load right over here, which is RL. So the output current that is going to the load is indicated by IO, and this current passes through the load, and therefore it develops the voltage across the load, which is output voltage or the load voltage. So that's how we do the schematic representation. What about some of the amplifiers when they are built with a single power supply? So what they have is this VDD, that is a plus positive supply. Input source is VI, that sources a current II, and then the output load current delivered by this power amplifier flows through the RL, which develops the voltage across this load, which is the output voltage. All right. So of course we have this output current IO and output voltage VO. So therefore, power is a multiplication of these two quantities. That is called output power. We have this input voltage and the input current II. Therefore, that forms the input power. And then there is a VDD, and it sources, this DC supply sources a DC current, let's say IDD, into the amplifier. So basically that forms the DC power. So what power amplifier does is it uses some of this power from the DC power supply and sources it, some quantity of it sources it to the load, output load. So that's how it converts that. So we'll see how it will define some quantities. Let's say define first is a voltage gain, which is the ratio of VO over VI, output voltage by input voltage. And the current gain we defined, which is AI, which is output current by input current, and power gain, of course. Power gain is basically the multiplication of voltage gain into the current gain, because we know that power is V into I. Okay, so we can write the voltage gain like this, and current gain is the ratio of the two currents. That's how we can determine. How about in decibel? So we define in decibel these three quantities. Voltage gain in decibel can be represented by 20 log magnitude of the voltage gain AV. Current gain in decibel is defined as, is calculated as 20 log magnitude of current gain. All right, and we have this power gain in decibel is calculated as 10 log AP. So we don't take a magnitude here, but however here we take a magnitude. All right, so the gain AV can have a negative value or positive value, and the current gain AI can also have positive value or negative value. So depending on whether the amplifier output is output of the amplifier is in phase with the input or out of phase 180 degree with the input. So if it is out of phase, the gain is negative, and the current gain is also negative. If the output signal of the amplifier is in phase with the input signal, So the current gain or voltage gain, they have a positive sign. So anyways, we take the magnitude. So obviously these signs are not important here. So let us understand now. Let us take a look at this schematic. What we see here is we have a power amplifier which has a gain A, and it is connected to the positive power supply, DC power supply, with the value VDC, and that sources the current IDC. Then we have the input signal VI that sources a current II, and then we have the output current IO that flows through the load, which develops the voltage across the load as VO. All right. So let us see how it works. So first of all, we can determine and calculate these three quantities. First of all, DC power, which is defined as PDC, which is the multiplication of VDC into IDC. So as we said before, this power amplifier's function is to utilize some of this power and convert it, utilize some of this power and deliver it to the load. So that's why, and we determine the power efficiency by that. Okay, usually the signal power, which is multiplication of VI into II, has a negligible contribution. And then input power, PI, which is a multiplication of input voltage and the input current. And then we have this output power, PO, which is the multiplication of VO into IO. Okay, so we have these three quantities defined over here. And now let us see how we can calculate the total power. So total input power is, which is given as P. So total input power is nothing but a summation of DC power, which is the VDC into IDC, plus the input signal power. All right. And we can represent with the formula like this. So usually PI is very, very small than VDC. All right. Because the input signal is in the millivolt and the current also is in a small range. So that's why we can have this. So input power, we can say that essentially P is approximately PDC. That's the input power. Okay. And the total power, let's say PT, we can write here. That is the total power, which is the, so neglecting this power, input power PI, we neglect it. So total power is nothing but how much power you have as an input, which is VDC into IDC, and then how much is dissipated into this amplifier, and how much remaining power is sourced to the load right over here. So what we see is the P dissipated plus the output power. Okay, that's the total power. And with this P is nothing but you have the total input power. Okay, so this basically is the same. We can always say that this is basically the same one. You can write here. Okay, so this is your P. All right. So P dissipated is the power consumed by the amplifier. So we can write this PDC plus PI, which is the dissipated power plus the input power, equal to P dissipated plus the output power. All right. So this is basically a power balance equation. And from this we can determine the power efficiency, which is eta, and that is the ratio of how much power is delivered to the load which is basically a PO, and DC power, which is PDC. And we can take the percentage multiplied by 100. All right. So this is how we dissipate. So in fact, we have always have a PDC. Let's say it's like a 100 milliwatt. Okay, and if we have the output power is about 10 milliwatt. Okay, so we can always say that we have 0.1 into 10, 100 is equal to 10% power efficiency. This power amplifier is 10% efficiency. So now let us take an example how to design amplifier, and if it is already designed with some specification, what we can understand. So there is an amplifier here. It has a plus minus 10 volt power supplies, as we've seen here in the above block diagram. This amplifier here is connected to the positive supply and the negative supply. So plus minus 10 volt is an amplifier. And then we have a sinusoidal input voltage, which is 1 volt. So let us take schematic here, right over here. So this is the VDD and minus VE. They are plus minus 10 volt. So we have this plus VDD, or we can write plus minus VDD, or we can write minus VEE and plus VDD right here. And this is the value plus minus 10 volt. And then we have input signal, that is V in, which is a 1 volt over here. And output voltage, sinusoidal output voltage for the sinusoidal input voltage is equal to 9 volt, which is right over here. And the load, that is RL, is given as 1 kilo ohm right over here. And now this amplifier is drawing a current of 9.5 milliampere from each of these two power supplies. So it means it draws the current of 9.5 milliampere IDD right here. And we can write here IEE. So these two current, they are equally 9.5 milliampere each from each of these power terminals. Now the input current of the amplifier is sinusoidal, because we have a sine wave input voltage. So the current signal is also a sine wave input signal. And this value has a 0.1 milliampere. All right, peak. So all the quantities, the voltages and current, we are indicating it by peak values. Okay. Now what is asked here? To find the voltage gain, current gain, power gain, power drawn from the DC supply, and the power dissipated in the amplifier, and finally the power efficiency. So we've just calculated the formulas, and we've got the basics clear with these. So let us one by one we can solve this. So how to calculate voltage gain? We know that it's the ratio of output voltage by input voltage. Output voltage is 9 volt peak divided by 1 volt peak. So it's a 9. Of course, it has no unit because both output and input are voltages. Now in decibel, we can always represent 20 log of magnitude of AV. So which is 20 log of 9, which comes out to be 19.08. Now next is to calculate current gain. How to calculate current gain is the ratio of two quantities, IO by II, and output current is not given, but we know what is the output voltage across the load. So load is given, which is the ratio of VO by RL divided by input current is also given. So we have this 9 over 1K divided by 0.1 milliampere, and that comes out to be 90. Again, the unit is not there because output current and input current is the ratio of these two quantities. And in decibel, we can write the current gain as 20 log magnitude of AI. That comes out to be 39.08. Now the power gain. Power gain, we know that is the multiplication of the two gains. So AV is calculated as 9, AI is calculated as 90, and total it goes to be this one. So again, the unit is watt. Of course, it's a gain. It's not the power. It's the power gain. So we can always write like this. So it's again unitless. In a way, we can always determine the power gain in another way, right? So output power, which is PO, the ratio of output power to the input power. So we know that what is input power, and we know that what is output power. So that will give us the power gain. So either we first determine the voltage and current gains and then calculate power gain, or we have this formula to calculate. So how to calculate output power? Output power, we know that P is equal to V square divided by R, or we can use I square into R, or we can use P equals to V into I. So one has to remember that the values given in the examples, they are in the peak values. These are the peak values. So what we need to take into account, we have to calculate the power, then we have to take the RMS values of the voltages and the currents. Okay, these values will be RMS values of the voltages and the currents. So right over here. Okay, so we see that output power can be calculated as, which is a power delivered to the load. We take this formula V square by R. So VRMS will be peak value, which is 9 volt. Output voltage was 9 volt divided by √2. Take whole square and divided by 1 kilo. So that comes out to be 40.4 milliwatt. Similarly, the input power. Input power, we know that that is a signal power. Okay. So it's basically an amplifier, okay? And you have a power output and you have a power input, right? So that's how the power gain will be PO by PI, input power. So input power is nothing but the signal power, which is the ratio of VI into II. And these values are the RMS values, okay? So RMS will be VI by √2 into II by √2. And we calculate it and it comes out to be 0.05 milliwatt. So as we can see that this power, input signal power, is very, very small, 0.05 milliwatt. Output power that has been delivered is about 40 milliwatt. So where from this power was generated? So we'll see that. So once we know that, we get the power gain, which is 800 into 10. 810, so it's quite big, and how we'll see in few minutes how this was achieved. So again we come down. Now one has to calculate, the next question was, we have to calculate power drawn from the DC supplies. So for the power drawn from the DC supplies is again voltage into current, so which is PDC. So we have dual power supplies, so VDD into IDD plus VEE into IEE. So we have these values, VDD 10 volt and VEE 10 volt. And of course, we take the magnitudes of these values, not the absolute values. So and the currents are drawn from each of these power terminals was given to be 9.5 milliamp. And then we evaluate it to be 190 milliwatt. So what we can see here, DC power supply is 190 milliwatt. Input signal power is 0.05 milliwatt, much less than the DC power. And the output power that was finally delivered to the load was 40 milliwatt. So what we've understood is that this power amplifier, it draws the power, takes the sum of the power from these supplies right over here, okay, and uses this power, or say converts this power to deliver it to the load. That's how it works. So finally, one has to calculate how much is the power dissipated in the amplifier. What is this? So when this amplifier is making some conversion, like using this some of the power from the DC power supplies to deliver it to the load, right over here, it has resistors, transistors, it functions, and therefore there is a dissipation into those components, which generates in the form of heat, and one has to calculate that. So how to calculate that? So we know that the total power is the DC power and the signal power. Again, we have this amplifier, we have this load over here, and what we have is this is the output power, and then we have this DC sources right over here, PEE, and these currents are being drawn here. So that is the DC power, and we have this input signal power, which is a combination of input voltage and the input current. All right, and there is some power right over here inside the amplifier, which is called as dissipated. All right, so how we understand this? The DC power plus the input signal power. So that is the total input power into this amplification system, and that equates to how much power was delivered to the load and how much was dissipated. So finally, so this is the power equation, and usually PI is very, very small. So we can just say that DC power equals to this, how much power is dissipated plus how much was delivered to the load. And one has to calculate it. So P dissipated will be simply PDC plus PI minus PO, and we simply plug in these values, 190 milliwatt, which is the DC power, and this is very, very small signal power, and subtract it minus 40 milliwatt. So finally it comes out to be 149 milliwatt. So we can see that these quantities, large amount of power gets dissipated into this amplifier in amplifying the input signal at a power level. So it amplified the input power level from 0.5 milliwatt to the output power level of 40 milliwatt, and it uses the power about 40 or 39 milliwatt, which is 190 minus 149, to achieve this job. So its efficiency would be simply calculated as how much was delivered to the load, the power, and how much was drawn from the supply. So which is calculated to be 21.2%. So apparently this amplifier is not that effective, but it does the job of amplification. So that's how we understand the basics concepts of this amplifier, and this is how the role